Welcome to this presentation. In this model, let us have an insight of aperture antennas. In aperture antennas, part of the structure of an aperture antenna is an aperture or opening through which electromagnetic waves flow. An aperture antenna operating as a receiver collects waves via the aperture. So unlike in acoustics of the megaphone and the parabolic microphone, which uses a parabolic reflector to focus sound waves on a microphone at the focal point. Also, the pupil of the human eye is an aperture for optical frequency electromagnetic waves. At radio frequencies, horns and reflectors are examples of aperture antennas. Aperture antennas are in common use at UHF frequencies and above. And they are the antenna of choice in applications requiring very high gain. Distinguishing feature of large aperture antennas is the increase in gain with the operating frequency. The gain of an aperture antenna increases with the square of the frequency if aperture efficiency is constant with frequency. Another feature is the nearly real valued input impedance. Since all the receiving antennas act as collectors of waves, an effective aperture can be defined for every antenna. However, antennas that have an obvious physical aperture will be now described, and general principles are developed for calculating the radiation patterns from any aperture antenna. And although the aperture antennas were not widely used until the World War II period, the basic concepts were available in 1690 when Huygens explained in a simple way. So an aperture opening as a receiver collects wave via the aperture, and the gain of the aperture antenna increases with the square of the frequency. Here are some of the advantages of aperture antennas. And the radiation is greater than the two-wire transmission line, and the radiation is omnidirectional. And the main disadvantages of aperture antennas are its VSWR increases and it has poor radiation. Aperture antennas are widely used in microwave applications and surface search radar applications. And Huygens explained in a simple way the bending of light waves, that is diffraction of light waves around an object. This was accomplished by viewing each point of a wavefront as a secondary source of spherical waves. The next wavefront is the envelope of these secondary waves in the forward direction. Some 150 years after Huygens' contribution, Fresnel recognized that the phase shift between wavefronts is computed from the distance between the wavefronts, delta L, by the familiar relation beta into delta L. So now let us see how a plane wave and a spherical wave can be constructed from a secondary waves. The envelope of the secondary waves forms the new wavefront. Geometrical optics predicts that light shining through a slit in a screen have a lit region and a completely dark shadow region with a sharp boundary between them. Geometrical optics works well only for the apertures that are large relative to a wavelength. The secondary source concept shows that the secondary waves will spread out away from the aperture and there will be a smooth blending of the lit and shadow regions. And this diffraction effect is for a slit in an opaque screen with a plane wave incident on it. Huygens principle evolved in the mathematical form referred to as the equivalent principle or field equivalence principle, and the field equivalence principle replaces an aperture antenna with the equivalent currents that produce radiation field equivalent to those from the antenna. The equivalence principle is derived by observing that a solution to Maxwell's equation and the boundary equations, and which all electromagnetic problems must satisfy is the solution. This follows from the uniqueness theorem in mathematics, which states that a solution that satisfies a differential equation, that is Maxwell's equation, and the boundary conditions is unique. We now use this concept to set up the equivalent current relations for use in analyzing the aperture antennas. So in the original problem, the fields that satisfy the Maxwell equations in the region exterior to the volume V and that satisfy boundary conditions along S are unique. As long as the source is exterior to V and the boundary condition along S and are not changed, the solution E and H will not change. So Huygens principle can be stated as every point on a wavefront may be considered as a source of secondary wavelets which spread out in the forward direction or the speed of light. The new wavefront is a tangential source of all these secondary wavelets. So this diagram shows the secondary wavelets from the primary sources. So here the figure shows how a plane wave and a spherical wave can be constructed from the secondary waves. The envelope of the secondary waves forms the new wavefront, and the secondary source concept shows that the secondary waves will spread out away from the aperture and there will be a smooth blending of the lit and shadow regions. Fusion principles evolved from the mathematical principle, as I said earlier. It is called as field equivalence principle. This is the diffraction effect for a slit in an opaque region with a plane wave incident on it. Okay. And in the equivalent problem, the sources exterior to V are not changed since they are none. And also the boundary conditions are not changed, as in the original problem the fields along the boundary are E of S and H of S. In the equivalent problem, the original sources have been removed, that is the antenna structure, and altering the field internal to S and is denoted as E1 and H1. In order for the fields external to S to remain the same, equivalent currents must be introduced to satisfy the discontinuity of the fields across S. These equivalent currents are found from the boundary conditions, that is Js1 is equal to n vector into H minus H1 on S, and Ms1 is the E minus E1 into n vector, where E1, H1 and E and H are the fields internal and external to S. These equivalent currents, which are obtained from only a knowledge of the tangential fields over S, can be used to find the fields external to S. And how the fields on S required to determine the equivalent currents are unknown. Also, we do not know how to find the external fields from the equivalent currents. Now, we address these difficulties starting from the second one. Since the internal fields E1 and H1 are arbitrary, we choose them to be 0 for simplicity. And if we choose it as a 0, then Js will become n vector into H of S, and Ms will be equal to E of S into n vector, where E of S and H of S are the fields over the surface. This 0 internal field formulation is referred to as Law's equivalence principle. Since the fields inside S are 0 in the equivalent problem, we are now free to introduce materials inside S. If a perfect electric conductor is introduced like this along S, Js will vanish, and this leaves the magnetic current density Ms radiating in the presence of electric conductor, producing the external fields. Similarly, a perfect magnetic conductor, here as you can see in this figure, can be introduced along S to eliminate Ms, leaving only Js. Thus, we have two more equivalent formulations. They are Ms in the presence of perfect electric conductor over S, and Js is in the presence of a perfect magnetic conductor over S. Both yield the correct fields external to S. However, these problems are difficult to solve as long as S is a general surface. And note that if the real antenna contains conducting portions, then the Js equals the actual current density over the portion, and the aperture portion contains both Js and Ms before any fixed conductors are introduced. So, if the surface S is large in terms of the wavelength and the curvature of S is small, image theory can be applied locally across the surface to solve the currents operating in the presence of introduced conductors. However, since the selection of S is for convenience and we are interested in radiation problem, we can extend S to infinity. Since S must be a closed surface, S includes the infinite plane along Z is equal to 0 and closes at infinity. To enclose sources in the region Z less than 0. In this case, we can apply image theory with no approximation and easily solve many practical problems with planar aperture. We can apply image theory in the planar surface to simplify the solution procedure. To do this, the fields due to currents Js and Ms on Z is equal to 0. Z is equal to 0 plane. This will be followed by the application of the image theory to reduce the solution formulation by 1/2. Right. So, although not all antenna problems have a planar aperture that can be placed in the XY plane, an equivalent planar aperture surface S can be set up. And this will be fruitful if the tangential fields over S can be obtained. And first we need to solve for the fields in Z greater than 0 due to equivalent currents. So here Js is the electric current density and Ms is the magnetic current density. If a perfect electric conductor is placed along this, Js will vanish as I said earlier, and the explanation is often given the electric current is shorted out by the conductor. Right. And these leave the magnetic current density radiating in the presence of electric conductor producing the external fields. And similarly, a perfect magnetic conductor can be introduced along S to eliminate Ms, leaving only Js. So the magnetic vector potential is found to appropriate to the geometry of the equation. Like A is equal to mu into e power minus j beta r by 4 pi r, double integral s js of r dash into e power j beta r dash into ds dash. And the electric vector potential F associated with the magnetic current density can be written as F is equal to epsilon e power minus j beta r by 4 pi r, double integral s and ms of r dash into e power j beta r dash into d dash. So the far field electric pattern E is equal to minus j omega into a theta into theta dash theta vector plus a phi into phi vector, and the far zone magnetic field arising from F is written as Hf is equal to minus j omega into f theta into theta vector plus phi into phi vector. Since the solution is in the far field, the electric field associated with Hf is given as Ef is equal to minus j omega eta into minus phi into theta vector plus f theta into phi vector. Now the total electric field is then found by summing the contributions from each current, and E is equal to Ea plus Ef, that is equal to minus j omega into a theta minus eta into phi into theta vector plus phi into eta f theta into phi vector. The equivalent system of this figure involves both electric and magnetic current densities. So then the radiation fields for Z greater than 0 are found by one of the three equivalent systems, and Js and Ms on S, E will be equal to Ea plus Ef. When 2J is on S, E will be equal to 2A, and 2Ms on S, E will be equal to 2Ef. We can now summarize the equivalence theorem in terms of the most suitable to radiation pattern calculations. First, an aperture plane is selected an antenna for the antenna, and this is usually the physical aperture of the antenna, but need not to be. And coordinates are set up such that the aperture plane in the xy plane and the z axis is in the forward radiation direction. Then the radiation fields for z greater than 0 are found by one of the three equivalent systems. And these three equivalent systems can be defined as the E is equal to Ea plus Ef, and E is equal to 2A, and E is equal to 2Ef. Thank you.